I'm pleased to open the second colloquium. We still have some technical problems, and maybe thanks areas that I thought that this will start half an hour later. The problems were not from myself. And but I think it's still important that it will be recorded together with the Mac technology is somewhat problematic. I don't think I need much introduction to Marek. In fact, I think he started. He got his PhD in Tel Aviv. He was in Stanford for several years after it. He came back, and since then is here. And he's a director of Advanced Study Institute here. He's I think chair in high energy physics. But that's the main thing. No, you have
not in high energy physics.
You have a chair. I am a chair in complex physics, but which is it doesn't matter. But he's a chairman. The chairman and the chair is not the same. It's chairman of some high energy physics in Israel, which was representative in CERN once. I don't think that Marek should correct me in all these things. There are more important things he should say. But what I do understand that he had some predictions pretty long time ago, which were experimentally found in recent years. And this big news, this is what we want to hear now. Please.
So thanks very much. It's a pleasure to give a talk here in my alma mater. And what I will try to do today is to give you an overview of some recent exciting developments in the field of hadrons, exotic hadrons involving heavy quarks. So the picture here is, you can see it, is a schematic picture of a tetraquark. I will explain it later on. And another way to put what we are doing is to say we are discussing the social life of heavy quarks. Who is whom, for how long? Is it a one-night stand, namely something which is unstable and decays quickly, or is it till death us do part, in the sense that these are semi-stable or even stable hadrons? Okay, so
can you take off this?
Can I take what?
The window. Take off these ends to.
I have no idea where this is coming from. It's not on my screen. Well,
thank you.
Okay, no? Yeah, okay. So a brief outline. Quarks, as you all know, are fundamental building blocks of protons, neutrons, and all hadrons. In principle, all quarks are equal in the sense that they have the same couplings to gluons, but heavy quarks are more equal than others in the sense that it's much easier to understand their dynamics, and this will take advantage of that. And the big experimental news in recent years is discovery of new combinations of hadrons, of quarks, forming hadrons with heavy quarks, including exotics. Most recently, a newly discovered tetraquark with 2 charm quarks and 2 light antiquarks. A very robust theoretical prediction for a stable tetraquark involving 2 big quarks, hadronic molecules, etc. And this is really like a new layer in the periodic table. So schematically, what we are talking about is, we start from crystals, we go down into molecules, atoms, atomic nuclei, proton, and we are discussing objects whose size we know is smaller than 10 to the minus 18 meters. They might well be point-like, but experimentally we know they are smaller than 10 to the minus 18 meters. These are quarks. Sorry about this. Yeah. So just a schematic plot showing the astounding range of masses of elementary fermions and also bosons in nature, going over a very large numbers of order of magnitude from 10 to the minus 15 or maybe below in GeV up to more than 100 GeV. The top quark is the heaviest and the neutrinos are the lightest, and we will be focusing in that region here in the middle. So this transparency is actually extremely important for us because it is thanks to that transparency that this department exists. Because Yuval Ne'eman, the founder of this department, made his big breakthrough by classifying hadrons containing 3 light quarks, discovered simultaneously and independently of Gell-Mann in 1961 that there is a unitary symmetry connecting them. Later on, Gell-Mann and Zweig understood that this is a result of all hadrons being built from then 3 quarks. Today we have 6 quarks, out of which 5 participate in hadrons. 1 is too heavy, so it decays too quickly to make a mark. So again, schematically, all strongly interacting particles, which are referred to as hadrons, are built from quarks. Proton is built out of 2 U quarks and 1 down quark. A neutron is built out of 2 d quarks and 1 U quark. A pi meson, pi plus, is built out of a U and an anti-D, and a pi minus is built out of an anti-U and a D. Baryons are composed out of 3 quarks. Mesons, such as pions, are composed of a quark-antiquark pairs. And in this plot, arrows denote quark spins. Quark carry colored charges, and the allowed combinations, the charges are non-abelian, and the allowed combinations are such that the physical particle corresponds to an object which does not carry net color. In technical sense, these are singlets under the color group. All right, now, the most important piece of information to keep in mind is the potential between heavy quarks. We know, it has been known for a long time now, that the potential between heavy quarks consists of a confining piece at large distances. It's linear confining force with a coefficient which we denote by sigma. And at short distances, it is Coulomb-like with fine structure constant alpha replaced by alpha S, which is the strong interaction coupling. But functionally, it's very similar to the Coulomb potential. And this turns out to be extremely important and crucial for the subsequent discussion. So here we have some animations which show how systems of a quark and antiquark behave, or system of 3 quarks, because of confinement. As quarks recede from each other, a flux tube of chromoelectric flux is formed between a quark and an antiquark, or alternatively, in the case of 3 quarks, a Y-shaped chromoelectric flux tube is formed between the 3 quarks. This is well known, and what we want to discuss today is the extension of this picture to hadrons, which are neither quark-antiquark or three quarks. These are the ordinary hadrons, and exotics are the ones which do not belong. In this here, you have, again, a beautiful simulation showing what happens as you take two quarks away from each other. At first, you see a string where a lot of energy is packed between these quarks. And then as they get far enough from each other, the energy packed inside the string is enough to create a quark-antiquark pair. And then the string breaks. So you can never isolate a single quark because of this mechanism. So to reiterate, standard hadrons are mesons consisting of a quark and antiquark, and ordinary baryons consisting of three quarks. Exotic hadrons do not belong to these two categories, and the simplest exotic hadrons are tetraquarks, which contain two quarks and two antiquarks, or pentaquarks, which contain four quarks and an antiquark. It's always the net number of quarks is always 0 modulo 3. Now, the fact that exotic hadrons exist was known, predicted as a possibility already by Gelman and Neyman. Many years ago, when they invented the quarks, they understood that such a thing is possible. But it was not clear whether this possibility is in fact realized in nature. It's a dynamical question whether you can take two quarks and two antiquarks and get a combination which is either stable or semi-stable. And only recently we have seen evidence that when at least two of the quarks are heavy, such a thing is in fact possible. So there is robust experimental evidence for multi-quark states, also referred to as exotic hadrons with heavy quarks. We have two kinds of tetraquarks, with a heavy quark and a heavy antiquark, or with two heavy quarks, and baryons with three light quarks and a heavy quark and an antiquark. So the two key questions that we have to pose to ourselves, both in theory and in experiment, is which additional exotics we should expect and how are quarks organized inside them. And by that, I mean, you have here a compact tetraquark, a small object. You can have one diquark and another anti-diquark, or you can have a hadronic molecule where you have two white color singlet objects like the deuteron. A deuteron consists of 6 quarks, which are organized into proton and neutron. So it turns out that all these possibilities are probably realized in nature, and some of them we have seen already. So the big experimental news came at the end of August in a conference and with a paper at the beginning of September, when the LHCb Collaboration at CERN announced that they have definitely observed a so-called charmed tetraquark, which I will explain what it is exactly, an object containing 2 charmed quarks and 2 light antiquarks. And the nice thing about it is that its properties seem to be very, very close to at least one theoretical prediction. So this is what they actually observe. This is a plot showing the distribution of the masses of 2 mesons called D0, which contain a charmed quark and a light antiquark and a pi plus meson. And we know that such a tetraquark, if it exists, this is exactly what it decays to. And the fact that this mass distribution has a very sharp peak here, very, very narrow, is a very strong indication that there is such an object and that it is very long-lived by the standards of hadronic physics. Okay, so what are the parameters of this object? Its width is very, very narrow as standards of hadronic physics go. It's around 300 MBKeV if you use a Breit-Wigner parameterization. In a more sophisticated parameterization, it's only 50 keV. So just to set the standard, ordinary hadrons have a width of tens or sometimes hundreds of keV. By width, I mean the inverse of the lifetime. And it's just a tiny little bit below threshold of two of these mesons, D0 star and D plus. Okay, so this was the seminar. Now, the first interesting question about these objects, after you establish that they exist, is how are the quarks organized inside them? So here we have two extreme examples. One is that you just put 4 quarks, 2 charmed quarks and 2 light antiquarks, anti-U and anti-D, you put them in a very small volume where the confinement does not yet set in. So the size of such an object would be about the same size as the proton. And that's it. And you can use theoretical toolbox to predict the properties of this object. And this is what we have done in 2017. Alternatively, you can assume that the 4 quarks, 2 quarks and 2 antiquarks, are organized into 2 mesons, which maintain their separate identities. And again, you can use theoretical toolbox or toolboxes to predict the properties of that object. Now, this plot was compiled by the experimentalists because they didn't know whom to believe before the object was discovered, so they kept track of all the predictions. And the green line is the actual measurement, and the red point is our prediction from 2017 based on this picture. The upper one, that it's a compact object, proton-like compact object. Okay, so my job, this is the list of the various papers. So my job today is to give you a rough idea of how it was done. And I hope I will succeed in that mission, but
Marek,
yes.
theoretically, you have some a priori understanding which of the two should be the one that will fit the experiment?
Well, I have it, and some other people have a reverse understanding.
No, not a posteriori. No.
A priori, yeah.
Why it should be the one and not the other? Because actually it's quantum mechanics, it's probably combination of things. But why mainly it's one and not the other? You have a system of 2 heavy, 2 light. Why should they organize themselves one way or another?
I understood the question. So I very much hope that in about half an hour, you will be convinced and you will get your answer why in specific cases, it's very clear what to expect. Okay?
All right, just to follow up on that question, of those two, you just jump ahead, which is more tightly bound?
the same answer as Shimon.
I can give mine.
No, if you want to give a talk instead of me, there is no problem. But we have a cutoff in time. If we continue like that, you won't hear anything. So one theoretical comment is that hadrons with heavy quarks are much simpler because heavy quarks have very little kinetic energy and very small spin-dependent interactions with each other. And this is the key to being able to make accurate prediction. So how did we do it? It's, in principle, what you would like to do is to solve the theory of strong interactions, quantum chromodynamics, and get your predictions. But nobody knows how to do that because it's a strongly bound, ultra-relativistic, nonlinear theory. So the best we can do is to use a phenomenological approach where you identify the effective degrees of freedom, extract model parameters from other experiments, and then use them to make the predictions. And we, as a warm-up exercise, in 2014, we used this approach to predict properties of objects which had not been seen until then, 2014. These were baryons which contained 2 heavy quarks, 2 charmed quarks, and 1 light quark, so CCU. And later on, we used it to predict the properties of the tetraquark, CC, U bar, D bar. And they're somewhat similar. Is there a problem, Lev?
Sharing the screen.
Well, it's here.
It's here. Yeah, Aaron is complaining that he sees like this. And maybe
I am sharing because it's showing here.
You can show only yourself. You can eliminate the others.
I have no idea.
Touch the right rectangle on the top of the people.
I think
As far as I know, it's
I think it's his problem. I see it well.
okay. So we apply the toolbox to baryons containing 2 charmed quarks and 1 light quark, and to tetraquarks, which contain 2 charmed quarks and a pair of light antiquarks. And they're somewhat similar because in both cases you have the same 2 charmed quarks. In one case, you have a fundamental color triplet quark, and in the tetraquark, you have a color triplet, a composite color triplet diquark. Now, doubly-charmed baryons are useful as a warm-up exercise because doubly heavy baryons are not exotic. They must exist. We knew it in 2014, and therefore they were an excellent testing ground for the toolbox. And in 2014, we published a set of predictions for the mass of the various doubly heavy baryons. In particular, for the lightest one, we predicted 3,627 MeV, and 3 years later, they found it at 3,622 MeV. 5 MeV off is, we thought, reasonably good. And that got us really going, and we decided that we should be able to use the same method for the tetraquarks. But before that, I just want to show you that it works not only for the mass, but also for the lifetime of this doubly-charmed baryon. The red band here is the experimental lifetime. This is our prediction, and this is the competition. Okay, people who tried to predict it as well didn't do so well. So what goes into this calculation of doubly-charmed baryon? The masses of charmed quarks, which are known. the coupling between the light quarks and the charm quarks, the masses of the light quarks. And the problem was, and this was the theoretical bottleneck, that there is no other place in nature before the doubly-charmed baryons were discovered from which you could extract the strength of the interaction between two charm quarks. So people were stuck for a long time, and out of, if you don't have anything better, you make an educated guess, which is what we did. We noticed that in the weak coupling, it's easy to convince yourself that the strength of interaction of two charm quarks is exactly 1/2 of the strength of the interaction of a charm quark and a charm antiquark. And so in 2014, it wasn't so clear why this should also be true in weak coupling. By now we understand, but then it was an educated guess. And once you make that guess, it's very easy to make predictions. This is the bookkeeping, the masses of the quarks, the binding, which is read off from charm anti-charm, just divided by 2. And everything else is taken from experiment. And this is the the 3627 MeV.
Okay.
Yeah.
Maybe it's irrelevant, but you draw the one gluon exchange, which is like the Coulomb force you alluded in the beginning of your talk. While for the CC bar, if I remember things from the past, when you described it in terms of a potential, it was not in the 1/r part of the potential, but it was in the log part of the potential, which extrapolate between the 1/r and r.
So indeed, the question was why, and by now we understand, and I will explain why this formula, which in principle applies in weak coupling, turns out to give a very accurate prediction. This is a very important point. Okay, so I'm going to skip this. So I will explain, not now. So the same theoretical toolbox that led to the accurate prediction for the doubly-charmed baryon mass can be utilized to predict the masses of tetraquarks. And it turns out that for doubly-charmed tetraquark, it predicts it essentially where it is, namely very close to the threshold. But quite dramatically, if you replace the charm by bottom, it predicts that the doubly bottom tetraquark is absolutely stable with respect to strong interactions. It cannot decay. It can only decay by weak interactions, which is big news. And to show you how this works, so excuse me. So this is the paper that was published, that was written, I think, a week after the experimental discovery of the doubly-charmed baryon. And this is a figure explaining the similarity between the doubly-charmed baryon, which is here, and the tetraquark, which is here. In both cases, you have two charm quarks sitting on top of each other, very close because they are heavy. Because of Fermi statistics, they must be in a state with spin 1. The two light antiquarks, again, because of Fermi statistics and because of energy considerations, the lightest state is spin 0. And so you have a prediction for free, essentially, that the quantum numbers of this object are spin 1 and positive parity. And this is, in fact, what they seem to be seeing. And for the bottom is completely analogous. So I'm going to skip that. I'm going to skip that. And so the point, going back to Schumann's question, when the two quarks are very heavy, they stabilize at a small distance from one another, just like if you take the hydrogen atom and you replace the electron by a muon, the atom shrinks by a factor of 200 because the radius is inversely proportional to the reduced mass. So when you have two very heavy quarks, like two big quarks, they sit essentially on top of each other at a distance of roughly 1/5 of a Fermi. And now, if you have two colored objects sitting at the 1/5 of a Fermi from each other, you're entering the realm of perturbation theory. That's the reason why the weak coupling works. Now, the really interesting thing that is happening here is you have this Coulomb potential. Alpha, the coupling is rather small, but since it's multiplied by 1/r, and r is very small, there is a big binding energy, hundreds of MeV, and this is what is making this object stable. So I'm not going to show you any more tables here, but this plot shows the distance from the two meson mass, which is called, in particle physics jargon, we refer to it as threshold. So this was our prediction in 2017. So this is the doubly bottom, which is deeply bound because that two of them are heavy. This is the mixed case, a bottom and charm is slightly below threshold. And then we predicted that the charm will be very, very close to threshold. We predicted that it will be 7 MeV above threshold with an error of 12. It turned out to be just below threshold. Our precision was never good enough to make that distinction. Now, I'm going to skip that. I'm going to skip that because you can estimate the lifetime, decay channels. I want to show you something else. Different kind of exotics. So these were the exotics with two heavy quarks. Now, what happens when you have a heavy quark and a heavy antiquark? In principle, they attract much stronger than a heavy quark and a heavy quark, but they only do that if you put them in a color singlet configuration, in a white configuration, and then they don't talk to the other guys. So you cannot form exotics this way. The only way you can form exotics with these heavy quarks and heavy antiquarks is if they are hadronic molecules, it seems. And in fact, here is an example of 5 such hadronic molecules which were known since the mid-2000s. And they all share some striking characteristics. Their masses are very close to the 2 meson thresholds. They have a lot of energy available for decay into charm, anti-charm, or bottom, anti-bottom. Nevertheless, they are very, very long-lived. We say in particle physics that they are narrow. And this is completely unnatural because the Fermi golden rule says that a lifetime of an object or the width of an object is the product of the available phase space times the matrix element. If you have a very large phase space, a lot of energy available, it should decay like that. But here you have a guy with 1 GeV of energy available for decay, and its width is tiny by standards of particle physics, 10 MeV. So there has to be a mechanism which prevents quick decay. And the only known robust mechanism which can do that is if these are hadronic molecules. Because what's happening? You have one hadron here and another hadron here. You have a heavy quark here and an anti-heavy quark here. and a light antiquark here and a light quark here. In order to decay into quark, heavy quark, antiquark, the two have to get close to each other, and the probability of that is very small. And this is what provides the semi-stability. So this was sort of understood. And then in 2015, we proposed that such a mechanism should apply not only to two mesons, but also to a meson and a baryon. Post factum, it's trivial, but somehow people did not think about it. And then once you say that, it's very easy to predict which combinations of a baryon and a meson should form such a hadronic molecule, which is basically an analog of a deuteron. Two hadrons which bind by not by color forces, but they bind by exchanging light mesons. And the lightest of these new kinds of objects is a bound state or semi-bound state of a baryon called sigma C and a meson called d bar star. And you can predict its mass because you say it's going to be just a little bit below the mass of the sum of the two objects. And we wrote a paper, and we were very lucky. Just few weeks later, it was discovered experimentally in 2015. Very beautiful experimental result. A textbook example of a Breit-Wigner. This is the amplitude in the complex plane as function of the energy. The technical name is an Argand plot, doesn't matter. But it was very nicely confirmed. And then in 2019, LHCb Collaboration refined these measurements. And now it's really extremely beautiful because now they see three states. They see one state near the threshold of this baryon and a D meson, which has spin 0. So that's natural that you only see one state. But then there is the threshold of this baryon and a meson with spin 1. Baryon has spin 1/2, the meson has spin 1. And so they can combine to form either spin 3/2 or 1/2 just by adding the angular momentum. And they see two very clear peaks, very close to one another. So there is, to simply put, there is no other reasonable explanation of what is observed right now other than the fact that these are hadronic molecules. And there might be some more, and again, I don't have time to discuss this. I'm going to skip that. There is some more additional. These are pentaquarks because you have a meson with a quark and antiquark and 3 quarks. And there's some new kind of them. It's really like a whole new periodic table. There is another guy with charm, strangeness, anti-U, anti-D. Again, I'm going to skip that. And finally, in the summer, the LHCb Collaboration discovered what appears to be a tetraquark, which consists purely of 2 charm and 2 anti-charm quarks. It is not stable, but it's fairly narrow. And so the picture is being filled in, and we expect several other states. So I don't want to go over time because maybe there will be questions also. So let me summarize what we have discussed. There is now a robust experimental evidence for a very narrow, extremely narrow, doubly-charmed tetraquark discovered by LHCb. which, going back to Shimon's question, could very well be a combination, a superposition of a molecule and a tightly bound small compact object. But this is only in the case of charm. In the case of doubly bottom, if you replace charm by bottom, there is no doubt that this object can only be a compact proton-like object. And the reason is that you can never generate the kind of binding energy that you have in the compact configuration. You can never generate it in a hadronic molecule, because by definition, in a hadronic molecule, the two objects are further away from each other than the confinement distance. And the binding energy is built on the Coulomb potential in the case of double bottom. So the doubly charmed baryon is found exactly where predicted. There is a robust prediction for double bottom tetraquark, which hopefully will be found by LHCb. Probably before they find it, they will find the bottom charmed tetraquark because it's easier, much easier experimentally. It's quite clear that the narrow exotics with a heavy quark and a heavy antiquark are essentially heavy deuterons or hadronic molecules, and there is many more of them that we should observe experimentally. There is an exciting new exotic spectroscopy awaiting discovery and understanding, the theoretical understanding. So I think I should stop here, and if there are questions, maybe we have some time to answer. Thank you.
Definitely have time for questions, please.
Marek, many years ago, you took a course from me, maybe in this hall, and you may have heard from me that any physics lecture should start with the Hamiltonian. What is the Hamiltonian that you are actually solving, and how do you solve it?
So, for the benefit of those who have not taken a course in quantum mechanics from Professor Aharoni, this was one of the very best courses that I took in my undergraduate years, and really superb. So the Hamiltonian is strikingly simple. The energy or the mass of a hadron is given by the sum of masses of quarks plus spin-dependent terms, which depend on the relative spin of the quarks, plus, in the case of heavy quarks, specific interaction between two heavy quarks, which is taken from another experiment. That's it. That's unbelievably simple.
So how many particles are in that Hamiltonian?
Particles. Quarks for every...
Yeah.
For every system, the quarks
Quarks that appear. So if you have a system of 4 quarks, you have 4 particles. If you have a meson consisting of a quark and antiquark, there are two particles.
So what do you do to solve that Hamiltonian?
No, you don't. So it's even simpler than that. All you do is you extract from another place in the experimental realm, you extract the parameters of that Hamiltonian, and then you just add them. I solved for you the Hamiltonian. That was the transparency, perhaps that wasn't clear enough. That is an example how you solve the Hamiltonian, okay? Just 1 second. I want to, since someone asked this question, I think it's a very... Okay. When I say that it's a phenomenological approach, the translation to Hebrew is bishul. Okay? We don't know how to solve this from first principle. All we know is to identify which are the relevant degrees of freedom And that in itself is a miracle because this is a system with an infinite number of degrees of freedom in principle. The fact that you can get a very accurate description with a very few parameters is not understood. I wish I could tell you why, but nobody knows why it is so. Now, the precision you estimate by comparing your previous predictions with experiment. This is where the plus minus 12 comes from. Okay. Did I answer your question?
Yeah.
No.
Just 1 second. It was Amir. Yes.
A two-part question. I don't understand why you're drawing the analogy to the periodic table from your molecules. I would have thought that the periodic table analogy should be your single particle. So the periodic table, that I would think it's a more natural analogy. So that's my first question. And the second question, is there any limit to how complex you can get? You have like 100 quarks.
The first question is very easy to answer. Strictly speaking, Shimon, excuse me, but
He's answering my question.
strictly speaking, it's not a periodic table of elements, but it's a table of the analog of table of nucleides, because every hadronic molecule is like another neutron. So you have all sorts of neutrons and maybe 3 particles together. And that the second part of your question, the answer is
That would be more than periodic.
nobody knows. Nobody knows how many you can stack together and still be stable. We are happy for the time being that the predictions, which involve 2 of them, seem to work very accurate. Shimon, you had a question.
No, that's because of the question of Amnon. I mean, the competition, which is a little boring, which really sort of start from first principles from
Lattice.
is the lattice.
Of course.
So what do the lattice do with respect to this? Because there you really start where Amnon wanted to start.
Absolutely. So lattice gauge theory, just for those who are not familiar with the concept, is in principle an exact method of attacking the solution of quantum chromodynamics by discretizing space and time and sending the spacing in the time and space direction to 0 eventually, and solving the theory numerically on a computer in a finite volume, and then sending the volume to infinity. What they know how to do as of now is the double bottom. They completely agree with us that it is deeply bound. By how much? There is some discussion whether this is 200 MeV or 150. Yeah, they compute it, but there are different groups and they differ from each other. And they differ by order of 40, 50 MeV. So it's an approximation of that. Now, nobody knows how to do reliably analogs of neutron on the lattice. It's very difficult because they are very large. They are very large, and this is an outstanding challenge, very beautiful. They are thinking about it, but so far, we have to use phenomenological methods. Of course, if we could solve the theory from first principles, it would be much better. Yes?
Do you have predictions for the doubly-charmed baryon? And do you know if LHCb are looking to it?
I have a prediction. They're not looking for it because it's hopeless experimentally in the next 10 years. Because, as you know, life of experimentalists is much more difficult than life of theorists. I can just sit down and calculate something. They have to sit and sift through enormous amount of data when there is not enough statistics for this. So, no, this is not something that we will see in the near future. Other questions? Yes.
Is there any possibility that there is a bound state that is bound not only against strong interaction, but also against weak interaction?
Well, quick answer is no. And the reason is you would like the binding, if I understand correctly, to come from strong interaction. So there is a proposal, very clever and interesting proposal from a physicist in NYU, Glenys Farrar, who wants to do exactly that. But what this amounts to is, neutrons are stable inside atomic nuclei because the binding is bigger than the mass difference between the neutron and the proton. So in order to make this thing absolutely stable, you would have to have the binding bigger than the mass difference, for example, between the strange quark and the up quark. And that is about 200 MeV. And all that we know about QCD makes such a possibility extremely unlikely. This is a fascinating question that I've spent a couple of days discussing with Glenys, but I'm very skeptical. Yeah, she wants it to be the dark matter. Okay.
That's been ruled out.
Should we thank Marek for
Thank
this
you.
beautiful colloquium?